Okay, so first of all, thanks for the opportunity of being here. This is also my first time, not only at ICTS, but also in India. So this is very interesting. I couldn't be here for the past 2 weeks. That's number one reason is teaching, and number two reason is that I was at a different workshop in the US. But looking at the program, there were quite a few talks on the non-equilibrium dynamics of quantum many-body systems in the past 2 weeks. And this will also be the topic of these 3 lectures that I'm going to present today, tomorrow, and on Wednesday. And the main focus of my lectures will be thermalization in closed quantum many-body systems. In closed and since these are supposed to be pedagogical lectures, I will be I decided to go a bit more for an overview character instead of like an in-depth character. That being said, if you have any questions or would like me to elaborate on any specific points, please do not hesitate to ask me. I'll gladly do that. Okay, let me give you a brief outline of how I'm planning this set of lectures. So lecture 1 today, that's going to be about some just basic notions. And then we'll be looking at the thermalization of integrable systems. Lecture 2 is going to be mainly about the thermalization of non-integrable systems. And I'll also try to at the end of lecture 2, come up with a set of kind of questions or research questions that I find are particularly interesting in this field. And then the lecture 3, that is going to be about the topic of irreversibility, or reversibility versus irreversibility in closed quantum many-body systems. This is probably the one where least is known among these 3 topics. Okay, now for today, so in general, I'll be mainly working on the blackboard 90% of the time, and I'll show some supplementary slides where appropriate. So first, I want to start with some experiments. That's for today. And these experiments are really the main motivation why this field has become so interesting for many people in the past, let's say in the past decade. Both the combination of the experimental possibilities and the fact that we have much better numerical possibilities for studying such systems. The second part is I want to talk about a related problem from classical physics, the Fermi-Pasta-Ulam problem. A notion that will play a role again and again in these 3 lectures is the question of integrability. And since these are pedagogical lectures, I will say a bit about integrable versus non-integrable quantum systems. Then very important is that we actually know what we are talking about. So we'll be looking at what we actually mean by thermalization in closed quantum systems. So that's definitions. And then if I get this far, the concluding part for today will be thermalization in integrable systems. And the key concept that we will be looking at is the so-called generalized Gibbs ensemble, GGE. So this is the outline for today. And I want to get started now with topic number 1, and that is kind of the experimental motivation why we are interested in studying the thermalization dynamics of closed, meaning isolated quantum N-body systems. So part 1 is going to be. Experiments. So, and the kind of the key experimental success that made this field interesting is the field of ultra-cold atomic gases. And I just want to give a few kind of highlights of what's important when we are dealing with ultra-cold atomic gases. So these are samples of atoms at temperatures of order nanokelvin. And so, of course, one of the spectacular possibilities in ultra-cold atomic gases is the possibility to form Bose-Einstein condensation when the de Broglie wavelength becomes of order of the interparticle spacing. What is more important for our purposes is that if one in optical lattices, so these are artificial lattices built by counterpropagating lasers, we can realize the same kind of physics that we have in solid state lattices if we are at temperatures of order nanokelvin, and this allows us to do many body physics with such cold atomic gases. And in order to do many body physics, we need, well, two main features, and that is we need to be able to work with interactions, and one of the nice features in many atomic species is that one can actually even tune these interactions by external magnetic fields using Feshbach resonances. So the details are not important for us, but the main punchline is that one has a lot of possibilities to manipulate interactions, and one can generate different lattices in different dimensionalities using these counterpropagating lasers. And from the point of view of these lectures, the most important property is that we have very good isolation from the environment. So, and this is a point that will come up again in a moment. So what this means is that we can consider these systems as isolated on timescales that are much larger than the interesting dynamical timescales of the system that we are interested in. Okay, so in consequence, what we have is an isolated or closed quantum many-body system with tunable interactions. And let me show you one slide. So here, yep. Can I come back to this question in a moment? Because I'm going to show the Kinoshita et al. Experiment where we can talk about this. So if I forget it, please remind me of it, but I'll come back to that. That is a very important question, and it will, yeah. Okay. So here is so just a picture of how this looks. This is from Emanuel Bloch's group in Munich. So what you see in here, that's actually this cloud of cold gases, of cold ultracold atoms. Here you see how with these counterpropagating lasers, one can create these artificial lattices using the AC Stark effect. So for example, here there's this ensemble of essentially one-dimensional systems that look like finite wires. And here's an example for how one can tune the interaction by tuning the external magnetic field. In this review here, this is a 2008 review by Emanuel Bloch, Dalibard, and Willi Zwerger. So the title of this is Quantum Many-Body Physics with Cold Atomic Gases. You can find a lot of details about everything that one can do using this kind of setups. Now, within this field of cold atomic gases, the experiment that really kickstarted the theoretical interest in thermalization dynamics of closed systems is this experiment by Kinoshita et al. And this has this nice title, Quantum Newton's Cradle. The reference is up there. So what is done here is that one is actually generating a situation very similar to this. So one has a lot of these one-dimensional, effectively one-dimensional systems. And in each of these, one is dealing with about 40 to 250 rubidium atoms. And now what is done experimentally is that, yeah. Sorry?
Quantum solution.
Yeah, exactly.
And also the previous slide does this mathematical expression for the linear model, just for applying for simply once.
Yeah, exactly. Yeah, exactly. So, what is done experimentally is that first of all, these each of these cylinders is sitting in an external potential, as depicted here. So the atoms in their ground state prefer to sit at the bottom. And what can be done now experimentally is that one splits this cloud and then two halves run up the potential well on each side. And then at some point they come back and they start colliding. And one can observe of order, if one looks at the experimental data, of order 30 oscillations of this kind. And this corresponds to time scales of about 10 milliseconds. Yeah, so order of magnitude 10 milliseconds. And so what they did is in order to so what they were interested in is calculating the momentum distribution function of these particles, and this is plotted here. So in order to understand what is actually shown here, one needs to know that at a certain point in time, they switch off this external potential, and then this basically cloud of particles expand, and then they take another snapshot sometime later. And this is what's depicted here. So at time t equals 0, so here you see that basically you have particles with large momenta moving left or right, because this is a snapshot of the particles sometime after switching off the potential. Yeah? So this is not the position of the particles, this is a map of the momentum of the particles. And so these are the kind of oscillations that one observes. So one can, up to 30 of these oscillations. After about 10 of these oscillations, these distributions become stationary and don't change anymore. And now what one can measure is the momentum distribution, that's the experimental data here, that emerges after many of these oscillations in essentially, from the experimental point of view, the steady state of the system, because on the timescales that are accessible in the experiment, nothing evolves anymore. And this is this black line is a fit to it. This is this line that you see here. And now we know very well what is the quantum mechanical model that describes the dynamics of these particles, and that's this Lieb-Liniger model down here. So here we have a kinetic term, and then we essentially have a delta action like interaction of these atoms that can be tuned by this parameter C. There's also the experiments have been done for various parameters C. So, and then of course one also needs to add the external potential, which is not shown here. And so one can figure out what kind of momentum distribution would you actually expect if you had this system in thermal equilibrium at a given temperature. And so, well, the best fit they could do is this dotted line here, and you can observe clear deviations from the experimental data. And waiting longer doesn't help. So the kind of tentative conclusion from this experiment is that on the experimentally accessible timescales, you start the dynamics, you wait, the system reaches something which looks like a kind of a stationary state, nothing evolves anymore, but the momentum distribution function is not one that can be fitted by assuming a thermal ensemble. Now, back to your question about the isolation from the environment, that needs to be taken, and that has been taken into account in the data analysis here, because you do have three-body collisions. So that means that you're actually losing particles, you have collisions with the background gas. So these things are taken into account. Yeah? So there are effects that come because you're never perfectly isolated from the experiment, but the associated time scale is kind of fairly slow, such that it is not too difficult to take this into account. And this non-isolation from the environment does not change the finding that you do not agree with a thermal ensemble. So that's a very good question. This Hamiltonian is, because we can tune these interactions so well, is, supposedly a very accurate description of the system. I'm missing the external potential, of course. Yeah, you can test it in other setups. But this Hamiltonian has specific properties. It's actually an integrable Hamiltonian, and that's part of what I will do later. And so that can be one part of the explanation of why this is happening. Another part of the explanation can be that this is a one-dimensional system. And even in non-integrable one-dimensional system, thermalization would take very long. So I'm going to be careful about that. But I think the issue is not that this Hamiltonian is not a good description. That does not play a role. That's been analyzed by them. So this is an ensemble average over all these pipes, all these cylinders. So it's not important here. Yeah.
Stefan, you probably mentioned this, but the experiment is in a trap, right? Yeah. So in the sense that when the cloud goes to the edge, it's really feeling non-integrability, right? The model is not integrable in a trap.
Yeah. The fact that, what I mentioned is that there is an external confining potential missing, and this external confining potential is also destroying integrability, as a matter of fact. That's why the analysis is actually a bit tricky. There has been very nice work done by Richard Koenig et al. On this model specifically with this kind of external confining potential.
Was that, are you trying to say something about integrable models here, or?
No. This is just experimental motivation. No. Right. I'm far away from integrable models. I'll get there later. Yeah, this is just the experimental motivation. This is basically what kickstarted this field, what made people excited. So the conclusion, or the tentative conclusion, would be that we have the experimental momentum distribution function is non-thermal. In the stationary state. And stationary state is here just defined as you wait long until nothing happens anymore, leaving aside the complications that you're not perfectly isolated from the environment, which of course if something is still happening, but you can deal with that. You're saying you're starting in the ground state. So that would be 0 temperature. Yeah. But then, you kick the system, so you have a finite excitation energy in your system. And then for this Hamiltonian, you can basically say, I'm interested in the momentum distribution function at a certain temperature if I write down the Gibbs ensemble. Okay. So so this is, of course, from an experimental point of view, a very specific kind of setup, where because one creates the system, has a high degree of basically the ability to isolate us from the environment. You can ask the question, is this maybe something very artificial? Interesting, but does this question of thermalization in closed systems also play a role in other kind of setups? Kind of coming back to your question again. So here, let's look at some experiments that have been done much earlier. This is just a more recent overview. This is time-resolved photoemission spectroscopy. So what you're doing here is that, well, first of all, photoemission spectroscopy is you hit a sample with a photon and you register the momentum and the direction of the photoelectron that gets emitted from the sample. And by doing that, you can learn something about the band structure of the system. This is, of course, a very old experimental technique. And now what you can do in time-resolved photoemission spectroscopy, so this is one overview, for example, is that you first hit the sample with an excitation pulse. So this is what's depicted here. So you kick your sample hard. So essentially what you're doing is you are exciting electrons in your system. So you are, for example, you are moving electrons from the valence band to the conduction band. And then with some tunable time delay, you do this probe pulse and you pull out your photoelectrons. So essentially what you're doing is it's like taking a movie of your system. You excite your system, and then with some time delay, you look at the distribution function of your electrons after the excitation. And of course, again, if you wait long enough, if this delay is large enough, then you would expect that basically, again, you're just probing the equilibrium distribution functions. Okay, and now this is one of the actually first experiments that's been done here. This is time-resolved PES on gold at room temperature. Without going into the experimental details, this is now the energy distribution function of the electrons in my system as a function of the time delay. So this is at zero, basically immediately at the time where I hit the system, or just afterwards. This dashed line is always the best possible, essentially Fermi-Dirac distribution fit that you can do to this distribution function. And you can see that this fit is not very good. You have a lot of electrons at higher energies. And this is exactly what you expect to happen if you excite the system. Yeah, you excite electrons, so you have much more electrons at higher energies than you would expect from any kind of thermal distribution. Now, if you wait for some time, so this is after 130 femtoseconds, you can still see there's a large excess up here. The fit gets a bit, well, it starts getting better if you wait longer and longer. And after about 700 femtoseconds, you can do a decent fit to the momentum distribution function in your sample with a fit temperature of about 1,300 Kelvin. Now, notice that 1,300 Kelvin is much, much higher than room temperature. So one way of looking at thermalization in the system would be to say, well, I have excited my electron subsystem, and because my electron subsystem is coupled to a much larger thermal bath, namely the lattice degrees of freedom, which have a much higher specific heat. So essentially, I would expect that the system, my electrons thermalize just by dumping the excess energy into the lattice degrees of freedom. But if this is true, then I would reach equilibrium at room temperature. This system reaches something which looks like a thermal distribution function at a temperature that is much larger than the temperature of the lattice degrees of freedom. Of course, if you wait much longer, then we are typically talking about a few picoseconds. Then this distribution function will now evolve towards such that its temperature equilibrates with the temperature of my phonon. So then I'll be at room temperature. But on these interim timescales, the system, the electronic subsystem, looks as if it is thermalizing, and without the need, basically without the help of some external environment. So there is a time scale here where this system by itself thermalizes. And of course, we know that there is also a time scale where the coupling to the environment becomes important. But for the thermalization dynamics that we see here, that time scale is not important. So even systems that are not so well isolated from the environment can, in the dynamics, show a behavior that can best be understood by thinking of them as the thermalization of closed systems. So this is time-resolved photoelectron spectroscopy. And so basically we can think of this as effectively an isolated system on timescales that are much smaller than the ones that are generated by the electron-phonon coupling. Different from the experiment, this quantum Newton's cradle, or this from the Weiss group, is that in this quantum Newton's cradle experiment, the isolated system did not seem to thermalize, whereas here, on the time scale where I can think of this as an isolated system, this system does seem to thermalize. Yeah? So we have two very different kinds of behavior, and obviously this is something that we would like to understand. So our kind of the goal that we extract from this is we want a dynamical justification of equilibrium statistical mechanics. So we ask the question, we prepare a system, an isolated system in some generic, we will have to say more about this later, initial quantum state, we wait for some time, and then we expect that if we have waited for some time, that we can describe the system effectively using equilibrium statistical mechanics. So, sorry, yeah? Sorry, this? Oh, this is a quantum Boltzmann equation. Yeah, this. No. I need to take into, so important for the thermalization here is the electron-electron interaction. Yeah. And then for the coupling to the phonons, we have the electron-phonon coupling, and then there's also phonon-phonon couplings that are not so important here because the specific heat of the system is so large. Maybe we can ask the question later. Yeah. Okay. So what we want is, so this is kind of the ultimate goal, is a dynamical justification of equilibrium statistical mechanics for closed quantum many-body systems. And let's kind of formulate this into three key questions that we want to understand. And the question number one, that's kind of where this experimental motivation was going to, and that's the question, what's the intrinsic time scale of a quantum many-body system to thermalize? Yeah? I'm not interested in time scales that depend on the coupling to the environment. There's always some coupling to the environment, but systems also seem to thermalize on the time scale that is independent of that coupling. So, what is the intrinsic time scale? What is the intrinsic time scale of a closed system to thermalize? The next question is, what are actually the conditions for a system to thermalize? Because we saw two different experiments, one that did and the other that did not seem to thermalize. What are the conditions for a closed system to thermalize. And well, and actually the first question that we need to address is, what do we actually mean by thermalization of a closed system? How do we want to define that? What do we mean? By thermalization of a closed system. So the take-home messages from this first part are that everything is somehow coupled to the environment, but systems also, at least some systems, seem to thermalize independent of the coupling to the environment. That's what we want to understand. What's the time scale? Does it happen at all? And of course, the first question is we need to actually define what we are talking about. Okay. Yeah. Oh yeah, yes. Yeah. That's yeah. No. I mean, this is a huge field now. Yeah. You can see that. I mean, it's yeah. I mean, of course, yes, you can see that. You can see that. I mean, for example, experimentally, this is one way of measuring the electron-phonon coupling. Yeah, which is important for, let's say, superconductivity, because you can basically you measure how the temperature difference between your electronic subsystem and the phonon subsystem evolves as a function of time, and that gives you access to this coupling, like an independent way of measuring this coupling. Okay, good. So this was the motivation, and now we will move on to part 2. And this is a problem from classical statistical mechanics, and this is the Fermi-Pasta-Ulam and Tsingou problem. So let me first give you a bit of the historical background of this. So this was essentially something that was studied in the 1950s. And initiated by Fermi in Los Alamos, and for obvious reasons, after World War II, there was an interest in computing in Los Alamos, and so Fermi was approached and asked, okay, can we do something? I don't think he was asked like this, but can we do something, different using these computers than simulating nuclear bombs? So what he suggested was, I think quite remarkably, well, we can do one thing with computers that the computer was called Maniac 1. We can do one thing with computers that I find very important, and that is I want a dynamical justification of equilibrium statistical mechanics in classical systems. So exactly the same question that we are now asking in quantum systems has been asked by Fermi for classical systems. And of course, for classical systems, you can do much more because you can just solve the equations of motion. You don't have to deal with an exponentially growing Hilbert space, etc. So you can do much more. The goal is the dynamical justification of equilibrium statistical mechanics in classical systems. And the model that they looked at is basically like this depicted here. So it's a chain of harmonically coupled degrees of freedom on a ring, and their equation of motion is written down here. So this first part is, of course, just what you would expect for a harmonic string. Yeah, so this would just give you oscillations, coherent oscillations with the various fundamental frequencies that you can fit into this ring. And well, because they were interested in the thermalization dynamics, what they included are anharmonic terms. Yeah, and these are the terms. This is the alpha term, and this is the beta term. This is the correspond to a cubic potential, and this is a Born potential. Yeah, and you also talk about the alpha FPU model and the beta FPU problem. So this is essentially the equations of motion that they studied. And what they did is that at time t equals 0, they excited the fundamental mode of the system, not too strong, and then they studied the subsequent dynamics. And if you would not have these terms, then of course this fundamental mode will just oscillate. But because we have coupling between the different modes, we will start pushing energy into the other modes. The results of this analysis were presented in this Los Alamos report. It's not a paper because Fermi actually died before this was completed. And for correctness, I added the name of Tsingou because Tsingou was actually the PhD student who did all the work and who was not on the paper. There, if you want to look at it, there was quite an interesting interview with Tsingou, I think I need to look it up again, not too long ago. So she's still alive. Yeah. Okay, so so this is the original report and a very nice, not super up-to-date review by Ford that I highly recommend. Physics Reports 213 in 1992. Okay, so, okay, now let's analyze, let's have a look at what the data showed. So what is plotted? This is from their original report. So what you see here is the energy that is stored in the various modes as a function of cycles. So cycle, that's just the period of the fundamental mode. So this is here, all the energy initially is stored in the fundamental mode. That's how you excite the system. And then you see, okay, well, because of these couplings, you start moving energy into other modes. Yeah, and that's kind of what you would start. This is what you would expect. You would expect the system to somehow equilibrate. I think this is either done with 32 or 64 particles. But then the surprise is that at 28,000 cycles, most of the energy goes back into the fundamental mode. And so this came as a big surprise to Fermi. It was completely contrary to what he had expected to find. And one can, of course, one can drive these simulations much further. If one goes further, then one sees that there's now less energy, that at 56,000 cycles, there is a bit less energy that returns to the fundamental mode and so on. So maybe you think, oh, I just need to wait really, really long. But then at some point, after waiting really, really long, suddenly you have again 99% of the energy in the fundamental mode. So the observation, certainly for them, is they do not observe a stationary state in the sense that this the energy distribution would become time invariant, and equilibrium statistical mechanics would predict an equipartition among all the fundamental modes, certainly for small alpha and beta. So that would mean that you should have the same amount of energy in all the modes, and this is not happening. So this is a situation where we do not reach equilibrium statistical mechanics. So partition. Well, for a system that is sufficiently complicated and non-integrable, you would expect that equilibrium statistical mechanics becomes applicable. I mean, that's the basis of how we do statistical mechanics. So you would expect that you reach a situation that you can describe using a Gibbs state. I mean, talking about a sufficiently large system, of course. Yeah, if you have a small system with just a few degrees of freedom, that's different. But here we are talking 32, 64 or more particles. So you would certainly not expect to find deviations that are so strong. Yeah, I mean, the energy is in the system, but the question is, how is the energy distributed over the different degrees of freedom? I mean, and you say it continues to do this. It never reaches a stationary state. Okay, we would need to look at this model. This is kind of different from the model from what I know, so I don't know if there's a specific reason for this. I mean, just for example, in this system here, if you excite one of the other modes, let's say the k=2 mode, or if you excite this mode with a higher amplitude, yeah? So if you have a higher excitation energy density in the system, then it does thermalize. So FPU thermalizes if you excite it a bit more. It just doesn't thermalize if you excite it in the way that Fermi-Pasta-Ulam did it. So it, you know, this is the generic expectation for a generic system. Yeah, I mean, so they were, in a way, they were lucky/unlucky, because the excitation which they used, it puts them basically in the regime where the system does not thermalize on the accessible timescales. I would think so, but I would need to look that up. Typically, you have smaller alpha and beta. So yeah, I would refer that question to the literature. Typically, you talk of smaller alpha and beta. Okay, so yeah, yeah. Yeah, that's the next part. I'm doing that right now. So yeah, exactly. So let's have a look at the explanation for this. And so the explanation is, well, essentially consists of two parts. It's the proximity to an integrable model, in combination with the K-M theorem. And so, so let me first briefly remind you what an integrable classical system is. So if we have a 2s dimensional phase space, so for example, if you have a one-dimensional system with s degrees of freedom, then integrable is defined as that we have s independent quantities that depend on the position and the momenta of the particles f mu. in involution. Which means that their buzzer brackets vanish. And where the first of these quantities is just the Hamilton function of my system. Yeah. So what this means is that all of these f's are conserved quantities because their buzzer bracket with the Hamilton vanishes. Okay. So these are all conserved. All f mu are conserved. And that implies that the dynamics of the system, of this integrable system, can essentially be solved by integration, by quadratures. Putting it another way, the dynamics is constrained by the fact that the allowed trajectories of my system must lie on on the phase space in the region that is basically determined by the simultaneous fulfillment of all these equations. So the first one would be just that the trajectory has to lie on the energy shell, and each of these higher constraints additionally constrains where the trajectories can lie. So, and in this setup, the system is obviously not ergodic. Ergodic means that the time average of an observable is given by the average over the corresponding energy shell. And this is definitely not the case because the trajectories cannot reach the whole energy shell, but are severely confined by all these additional conserved quantities. Yes? Yeah, well, I'm assuming S larger than I think 2 or 3 here. So yeah, you're perfectly right. I mean, if I have, of course, if I have a system where I have only one conserved quantity, well, then it's automatically ergodic. But the moment I have more than one conserved quantity, it becomes interesting. Yeah, yeah, that's true. Thanks. Okay. Okay. So now the observation, or what people found out about this Fermi-Pasta-Ulam problem is that it is, let me only look at the alpha FPU problem. The alpha FPU problem in the continuum limit where you make this a continuous system can be mapped to a KdV equation. Let me just write down this equation. It's a nonlinear partial differential equation. That describes shallow water waves. And it is an integrable PDE. And its dynamics describes, so this is taken from this review by Ford, what is shown here. So here they numerically integrate the KdV. And so the initial perturbation of the system is this dotted line here. So this is the fundamental mode that's excited. And then what happens is that this fundamental mode starts breaking up into these features that you see here. And what these features are, these are solitons. So solitons Soliton Solutions, so these are nonlinear waves. Nonlinear waves that propagate without changing their form. Without changing their form. Their velocity is proportional to their amplitude, so that's very different from what we have in a usual harmonic chain. And it's quite surprising that these things exist in the first place. And if they interact, they keep their identities after the interaction. So the solitons, they say one soliton is catching up from behind, and then they interact, and if you wait long enough, then again you have two solitons. And so basically they keep their form, and which keep their form after interactions. And this is a nice way of understanding this, what happens in this Fermi-Pasta-Ulam problem, because now your initial excitation, basically, you decompose it into the various solitons, they propagate with different speeds, and then when two of them come together, you have a recurrence, yeah? And these are these recurrences that we saw before. So if the solitons happen to be meet at the same point again, then you again have a recurrence and you have the energy in your fundamental mode. So this is part of the explanation of what one sees in this Fermi-Pasta-Ulam problem. This is exactly true in the continuum limit. Of course, FPU is a discrete lattice version, so it's not exactly an integrable model. But we expect, hope that because of the KM theorem, because we are close to an integrable system, that this structure is going to survive, even if we weakly perturb an integrable system. The question whether the Fermi-Pasta-Ulam problem with the initial conditions that were first used by Fermi-Pasta-Ulam-Tsingou eventually does thermalize on some long time scale is to date not resolved. So I just asked one of the experts. So even such a simple classical system, we do not know for sure whether it thermalizes or not if we wait long enough. What we do know is that if we excite it more strongly, that it does thermalize. That one sees easily numerically. But of course, if you start exciting the system more strongly with shorter wavelengths initial conditions, then the continuum version becomes a less and less good approximation, and then it's not so surprising that the dynamics is not just given by the integrable dynamics of the continuum version. So this question with the FPU problem is still not completely resolved, at least for the small excitation energy. However, the time scale where it might thermalize is astronomically large. So once we start approaching the age of the universe, we are not so concerned about this anymore. But it shows that even in classical statistical mechanics, the dynamical justification of, the dynamical justification of empirical statistical mechanics can be a pretty hard problem. And in quantum systems where we deal with an exponentially growing Hilbert space, obviously this is going to be much, much harder to make statements. Yeah? Yeah, that's basically by Anderson diffusion. or what was it called? Thouless diffusion, I think. Or I think Arnold diffusion. Arnold diffusion. Yeah, yeah. Yeah, no, I mean, I just asked 2 weeks ago one of the experts on this field, and his statement was different. So yeah, and I'm not an expert on this field, but I mean, yeah, you can dig into the literature. So from what I understand, it's still open. Maybe some people have different opinions. Yeah. Okay. Good. Okay. So now let's move to the next part. So we have seen that for classical systems, it's very important to take into account if they are integrable or not. And this is obviously also going to play a role for what we are interested in, namely closed quantum many-body systems. So let's have a look at integrable versus non-integrable. And so the question that you can ask, for example, can, in a similar way, quantum integrability be the explanation for this Kinoshita et al. Experiment? Yeah. So we first need to figure out what is quantum integrability. And the first thing to say is there is no unique definition in the literature what you mean by quantum integrability. This is a statement that I inevitably make at some point. I like to emphasize that definitions are not right or wrong. They're definitions, they are useful or not useful. Yeah? So we need to figure out what's a useful definition for quantum integrability. And the basic problem is explained very easily. If we have some Hamiltonian, some many-body Hamiltonian that I'm not going to write down, that obviously I can diagonalize this and write it in the energy eigenbasis. So I have dimension of Hilbert space mutually commuting conserved quantities. Namely, all the projection operators on the exact many-body eigenstates. Yeah, they're all conserved and they all commute. So that's many more than we have for the classical system, and it's also completely useless. Yeah? Then every system is integrable, and this really does not. It's not a helpful definition because it doesn't help you to classify anything and doesn't help you to solve anything. But this observation is kind of the basic reason why it is not. It's not just, you cannot just carry over the definition from classical systems. For people interested in knowing more about the possible definition of quantum integrability, I will write down a reference to a nice review by Jean-Sebastian Coe et al. So, Sebastian Coe and J. Mossel. And I'm sure it's also published, but right now I only have the archive number. Archive 1012-3587. And they give a nice overview over about 10 different definitions of quantum integrability and how they are related. And maybe the most important one is, essentially that we have non-diffractive scattering, or Yang-Baxter integrability, or Beta-Ansatz solvability. So non-diffractive scattering is essentially what you saw in the classical context with the solitons. Yeah, you have things that scatter, and then if you wait some time, you get them back. Yeah, because it's in one dimension, the only thing that can happen is that they exchange their momentum. And that is generalized to quasi-particle scattering in one dimension, and that's what you mean by non-diffractive scattering. Okay, so if with this, what emerges here is that you have macroscopic number. And so this is of order the lattice size. Of local conserved quantities, or let's call them conserved charges IN. And what does one mean by that is, well, they can be written as sums over local terms. Yeah, so for example, so I1 would be the Hamiltonian itself, so that, let's say, with the spin system, that would typically, is a sum over terms that contain nearest neighbor spin interactions. Yeah? And then let's say a quantity like I3 is a sum over terms that maybe contain spin interactions that live on 4 adjacent sites or 5 adjacent sites. So these can be written as sums over densities that only act on a certain number of adjacent lattice sites, and this number of adjacent lattice sites grows as n becomes larger. Yeah? So the underlying densities for the conserved charges basically act on more and more adjacent lattice sites as n becomes larger. So this is a useful definition of quantum integrability because it allows you to solve many problems. I mean, you can, for example, if it's beta-ansatz solvable, you can figure out the thermodynamics. You still can't figure out everything, yeah? You cannot, for example, easily calculate correlation functions away from a low frequency limit. Okay, and then another definition is to look at level statistics. And so level statistics is that you look at the spectrum of your many-body Hamiltonian and you do the statistics of the mean level spacing, of the energy level spacing with respect to a mean level spacing. So this is one paper that I pulled out, where they looked at, so this is An integrable Hamiltonian is the XXC spin chain with some flux. So this is integrable, and you can basically write down these conserved charges. And this, if you add this term with this J2, this is a next to nearest neighbor interaction, then it becomes non-integrable in the sense that these conserved charges cease to exist. And what is plotted here is the level statistics. So that's basically the question. If I have one energy eigenstate of my system, with what basically probability do I find the next many-body eigenstate in units of the mean level spacing? And what you observe for the integrable system, J2 equals 0, this term vanishes, is that you have a high probability of finding levels that have the same energy. Yeah? So you have no level repulsion. Yep. Yeah. Yeah. Right. I think it's just proportional. From what I know from the various systems that I know, I think it's just proportional. Yeah. No. It is not. No. It's, I mean, if you have a system with n latticide, let's say a system is periodic with n latticide, then you will typically have conserved charges up to in. Okay. So now what happens is that as you start turning on the non-integrable perturbation, immediately you get level repulsion. So you don't find degenerate energy eigenstates anymore, and you cross over into a different distribution. And now the statistics is, so we need to look at this, that's very important, away from the ground state. And one needs to take into account all the symmetries of the system. I mean, if you have some translation invariance or rotational symmetry, then you need to make sure that you only do your statistics within one of these conserved subspaces. Otherwise, you will immediately have degeneracies. So you need to take out basically all the obvious degeneracies. And then for integrable systems, because you have all of these higher conservation laws, you don't have level repulsion, and the statistics is Poisson statistics, and that is E delta E 1 over delta E to the minus E over delta. So there's no level repulsion because we have additional conservation laws. Now, for non-integrable systems, so if you look at these systems here, the level statistics is like this. For non-integrable systems, what one observes is what's called Wigner Dyson statistics. So that is the level statistics of random matrix ensembles. And for our purposes, what we need is that the distribution functions have a characteristic form E divided by the mean level spacing E to the minus A beta E squared by delta squared, where beta can be 1, 2, or 4. That's the 3 allowed numbers. And these coefficients alpha, beta, and beta are known. I just don't want to write them down. Yeah? And this is the orthogonal ensemble, this is the unitary ensemble, this is symplectic ensemble, and that depends on the underlying symmetry, time reversal invariance of the Hamiltonian. All of them show level repulsion because the probability of finding energy eigenstates that are degenerate goes to 0. That's generically what you expect if you couple two energy levels, then just a 2 by 2 matrix, they split. And here, if you look at this, at what happens as they turn on non-integrable perturbation, you see that this fully drawn out light, that's the Wigner Dyson distribution, and you start approaching this pretty well. And just as a remark, these distributions, both the Poisson and the Wigner Dyson distribution, that's parameter free. So you can't fit them any further. Yeah? They are uniquely determined by the mean level spacing, and that's something you pull out of the spectrum. So these are parameter free fits that you see here. So this is another possible definition of integrable and non-integrable. It's basically looking at the level statistics. Yeah? This is a definition that I actually like a lot. It's my favorite definition. Okay, so here for this, for here, yes. Yes. I mean, I mean, this, of course, this integrability holds for large systems. Yeah, so I mean, n is large, then e to the n is even larger. Yeah. Yes. Yeah. Yes. Good question. Yeah. I mean, I actually refer to this paper. One of the authors here was Andy Miller's. And so they try to specifically answer this question about the crossover. Is there something in between Poisson and Wigner Dyson? And it is because everything here, what you see here is of course a crossover in a finite system. And if I remember correctly, their kind of careful conclusion is that if they look at the scaling of their data, they seem to say there's no indication of a crossover when the system becomes infinitely large. So they would probably argue that it's either one or the other in the infinite, in the thermodynamic limit. I mean, there is one exception where you have different statistics. That's if you look at Anderson localization, if you are just at the transition. There you have also a universal level statistics that's not Poisson or Wigner Dyson, but that's a specific case for this ordered system. For these interacting systems, I think the expectation would be that it's only one or the other in the thermodynamic limit, but that's hard, of course, to pull out. And you need to be away from the ground state. Yeah, this is only true somewhere in the spectrum, but not close to the ground state. Well, you look somewhere in the middle of the spectrum, or at least away from the ground state. So you have your, let's say here you have your levels, and you figure out the mean level spacing in some energy window, and then you basically plot the statistics as a function of the mean level spacing. And if you do this carefully, then you also need to take into account, of course, you want to have lots of data points, but then the mean level spacing is also going to change, so you need to take that into account as well. And this is all taken into account. To do this really properly is a bit more difficult than one might think at first. But I mean, we've done in some related studies in my group, we also came across, the question of looking at this level statistics. And with today's computers, I mean, it's pretty easy to see one or the other. I mean, at least to see the indications. It happens pretty quickly. If you want to see it's not Poisson or it's more likely Wigner Dyson, it's nearly a bachelor project, I would say. Do that numerically. Okay, I don't know this result, so I would need to look at it. But of course, one needs to be careful in how one formulates this. I mean, for example, if you have a system of harmonic oscillators, you can create any spectrum that you want. You just draw the, the frequencies the way you want to, yeah? So you can do whatever you want. And I know there are counterexamples to this classification. Yeah, so I don't know the one that you mentioned, but this would be kind of, I think, like the generic expectation. But yeah, I mean, one needs to be careful. Yeah, I agree. With respect to level statistics, I'm not aware of it, but I can tell you where the problem would be. The problem would be is that your excitation is very close to the ground state. And close to the ground state, you typically would find Poisson statistics because you have quasi-particles, well-defined quasi-particles that only weakly interact. So the expectation would not, I mean, so it would be very hard to say something about the level statistics in the energy window that you're interested in for the original, if you quantize the Fermi-Pasta-Ulam problem. You could certainly say something for the higher energies where the system thermalizes. I'm sure you would find Wigner Dyson there. But in the regime where it's really interesting, that's close to the ground state, and then these statements don't work. Yeah, exactly. Yeah, exactly. I mean, they propagate, they don't change their form, they scatter, and they retain their identities afterwards. Yeah, and if you think about it in one dimension, the only thing that can happen then is that they exchange their momentum. Yeah, so that's very simple. You can't redistribute your energy. Yeah. There was another question, I believe. So I didn't get as far as I had wanted to, and I'm kind of happy about this because there were many questions. So tomorrow we will continue here, and we have kind of a bit of the background together, and we'll start asking the question, okay, what do we actually mean by thermalization? What do we want to mean by thermalization? And and then after that, we will address the question of, okay, so what now happens in an integrable system and what happens in a non-integrable system? And we'll see that there are big differences. Okay, so that's the agenda for tomorrow.
Thanks, Stefan. Do we have any further questions? I have one big question. So you showed us, okay, applying the classical definition of integrable system to quantum mechanical system is kind of stupid. What about the reverse way? I mean, these definitions, do they make sense classically? Can you?
Yes, they do. They do. Yes, they do. Yeah, you could, I mean, kind of coming from here, this, I mean, the conserved, I mean, basically this conserved quantities that you have in classical systems, from what I remember, they start involving more and more position and momenta of particles if you go to higher conserved quantities. So that would kind of correspond to what we have over here. Yeah, so I think the answer would be yes. Yeah.
So regarding this definition of macroscopic number of conserved charges, so does the interactions or the range of the interactions not matter for what is macroscopic, and also especially if you have not a lattice system but a continuous system, this is somehow
integrable systems, integrable quantum systems tend to only have short-range interactions. I mean, so that's basically experience. I mean, if you have, let's say, you look at a spin chain, what are integrable spin chains? They are the ones with next nearest neighbor interaction. The moment you start adding, let's say, next to nearest neighbor interaction, you lose the integrability. I mean, I'm sure one can come up with some artificial models that are different, but generically, this would be the expectation. Yeah. Sorry? Yeah. Yes, you have spin. Yeah, you have various spin models where, again, by adding, let's say, further spin interactions, there are specific points where they become integrable again. Yeah. Yes. But then if you go away from that, then again, they lose their integrability. So there are specially tuned models where this is not true. Yeah.
Just one question, two questions actually. One related to the previously asked question. If you take infinite range interactions, then mean field kind of becomes exact. So is it only at infinite range, like, or can you have a very weak power law and then it's still integrable? Or are there examples of? And again, asking the same question: is it just 1 or 0 infinite range or non-infinite range, or is there some gradual approach to that?
I mean, I would usually argue that mean field becomes exact in an infinite range limit, because that's where you can really show that you can the corrections become suppressed in some way. If you have very long range interactions, I would expect to find the same physics that I have in the mean field limit, but at least I would not know how to show how the higher order terms beyond the mean field limit are actually suppressed in this case. So I think, strictly speaking, if you really want to put a bound on the terms that you throw away, that I can do for infinite range models.
And I had a second question which was related to the level statistics, a more technical question.
I mean, I think there might have been an answer to your first question here. I don't know, because did you want to say something about that? Well, doesn't necessarily mean that. Exactly. Yeah. Because I mean, you map it to a classical model, and the classical model can very well be non-integrable. Yeah, absolutely.
A second question, more technical, about the level statistics. This fact that the mean spacing keeps changing. So there are people have said that you should look at the ratio of 2 level spacing.
Oh, yeah, yes.
Is that a good way? And this is a more technical question, or are there better ways to keep track of that shifting mean level spacing?
Yeah, there are better ways of studying the level statistics. There's other predictions that you get the stiffness of the spectrum and so on that come out of these random matrix ensembles. And from what I know, they are actually somehow easier to analyze than the level statistics. Yes. Yeah. So I mean, that is true. There are other quantities that are numerically better to look at than the level statistics, from what I understand from what the numerical people say. Yeah.
Question? Excuse me. Question? Yeah.
Sorry.
So, right. So about the first definition of this quantum integrability, you said that there are these order n local in space conservations.
Yeah.
Right? Is the local in space important simply because you're considering short-range Hamiltonians, or is there a deeper reason for it?
I think that it's hard to say what is a deeper reason. So I think it naturally comes out of these integrable models that typically have fairly short-range interactions that one has this structure. It also comes out of how these conserved charges are constructed. So it is, I think for these models, it's natural. Yes, I would say for these models, it's natural.
Okay, we'll have one last question and then all the other
questions. So there are many different, you gave many different definitions of this integrability. So how, should I take it like if any one of them is satisfied, this is integrable, or should I take it as?
Definitions are useful.
No, but so suppose one thing does not work, but other thing works. Then should I call it integrable or non-integrable?
Now then you need to say with respect to this definition it's this, with respect to this definition it's this, and it would be an interesting thing to study, because usually these definitions fall together. Yeah, I mean, so if you have a situation where the definitions don't agree, I think it would be very interesting looking at this and trying to figure out what's going on here, because typically they fall together, but you can come up with counterexamples. I think, you really need to say with respect to this definition, it's this, or this is what I observe. Yeah.
Okay, so let's thank Stefan again. We have